We're still doing TCP. So now, where are we? We're at the transport layer. We are trying to get data between an application on one computer and an application on another computer. We want to make that connection reliable, and we want to make it fast. So in previous video, we have introduced mechanisms like the sequence number and acknowledgement number. And we had this idea there might be a timeout. Let's get a reminder. So we've got a sender, we've got a receiver. That's a very wonky N, isn't it? Let's fix that up. So we had the sequence number, the SEQ, and the acknowledgement number. I'm going to pretend these are just integers. They aren't in reality, but let's pretend they are. In a crude model, we would send, this is our data, and this is the data with sequence number 1. And I'm going to leave a bit of space here, and you'll see why. And I'm going to send back an acknowledgement to say that we've got that data. But that is going to be really slow if we just send one packet of data. So a packet of data, around about 1,500 bytes. It's not a lot of data. And if you send one of those, wait for acknowledgement, send another one, wait for an acknowledgement, it's going to be horribly slow. What we want to do is send a lot of them together. So 1, 2, 3, 4. So that would be, so here's our dream. We send these 5, and then we acknowledge 5, and that acknowledgement is a cumulative acknowledgement. We're saying, all right, we've got everything up to 5. Now, this, we can call it a flight of packets. So the flight, or the packets in flight, the ones that we haven't yet got an acknowledgement for. So you as the sender, what you can be sure of is you've sent this many packets. Well, as far as you're aware, they're out there in the world. You don't know how big the network you're connecting to is. Because remember, you've got to connect to everybody, right? They may be in Melbourne, they may be in Beijing, they may be just next door. There may be a huge, wonderful fiber connection, or there may be some horrible bit of wet string that can take like 2 bytes a year. And you've got to operate with whatever that is. Maybe it's going, via a satellite, and it's going to take a long, long time. How do we deal with the fact that we don't know how big that network is? We don't know how long it should take for this to come back. How can we do that efficiently? There's 4 congestion mechanisms. And also, there's the problem of this round trip time. What we want to do is detect when there's congestion on the network. But the network isn't, it's not like they've got a congestionometer like the motorway saying, slow down, queues ahead, yeah? What we need to do is have some mechanism that's going to kind of automatically do that. So what sort of things might we use to signal there's a problem?
Well, I'm guessing you're going to have to time how long it takes for the acknowledgement to come back.
Yeah. So that's really important. So we call this the RTT, the round trip time, and that round trip time is really crucial to us, right? So that's one thing we can certainly do, right? So beyond the round trip time, there's a few other things we might do, like,
Yeah, well, you could look at what else is going on, previous kind of experience.
Yeah, absolutely. So we can look at the previous experience of our round trip time. So we start to get into this world where we are measuring the round trip time and saying, is it fluctuating? The RFC we're dealing with, RFC, remember, is our rules, our request for comments is the kind of Bible for us internet people that lays down our rules. And here we're dealing with RFC 5681 about congestion control. Now, the TCP standards lay down certain things you must do. They've got this kind of lovely language where it's, you should do this, you must do this, and you may do this. There's kind of a hierarchy. Some things in transmission control protocol are must, some things are may. There's a bit of flexibility, we call them flavors. So as life develops, as the internet moves on, we change the flavor of TCP we're using. Nowadays, almost everything is using a flavor called cubic. It's the most popular one now. And the flavor is really about how we're going to respond to these signals. When do we say that a packet is lost, and how do we respond to that? The main mechanism we have for response is this idea of a congestion window. Now, last time we were doing this, we put this window and I said, not that window. By window, we mean the amount of packets that we have out there in the network. So it's the number of bytes we believe the network can handle. There's two windows, and I'll deal with this one real briefly because it's not actually that important. So this window is our receiver window. So in the early days of the internet, the receiver would probably be in the same lab as you, just for the sake of the experiment, and maybe it's running a bit slow, so it's saying, oh, hey, I've got room for 100 kilobytes of data. Do not send me more than 100 kilobytes. I won't be able to deal with it. And that is sent in the packet header, so it's telling us you don't want more than this many bytes of data out there in the world, or your receiver might have to throw them away anyway because it can't cope. That's not actually really that important or it's not as important in the world as the congestion window. And the congestion window is kept track of by the sender and the receiver, and they're constantly tracking and thinking, how much data do I believe this network can send? There's two signals we could look at, and most of them just look at a loss signal. So most TCP variants, they're just looking, has a packet actually got lost? Yeah. So these acknowledgements have numbers, and if we don't get an acknowledgement, if nothing comes back, or we also said if the wrong number of acknowledgement comes back. So let's imagine this packet 2 dies. What I do then is to communicate it. So here, this is 2, this is 3, 4, and 5. Packet 2, it's got lost somewhere. So in fact, what I'm going to send back here is ACK1, ACK1, ACK1 again. So I keep saying ACK1. I have received packet 1. I've received another packet. It wasn't what I wanted. Yeah. Remember, we can't communicate too much information on these things. It's important to keep in mind this. We can't say anything complicated like, I've received packets 1, 3, 5, 7, and 8, but I'm missing 2, and could you please...
Too much data.
It's not how this mechanism is designed to work. This is all living in a header. We don't want to be sending a telegram worth of information. We want to send the minimum possible information to get our job done. That's why we're using kind of obscure signals. There are other mechanisms that can do that, not time to get into them. So we're sending this ACK1, and we're sending it repeatedly to say, this packet 2 is missing. By the time we get our... So we've got an ACK1 here, acknowledging sequence, packet 1, and 3 more of them. This is a triple duplicate. And now we suspect, probably something bad has happened to packet 2. Some things I need to do for that. Things I need to do for that, obviously, packet 2 needs to go out there again. But now I need to think, am I overwhelming the network? Am I sending out too much data? Now, even worse than receiving a triple duplicate, maybe I send them all out there, nothing comes back. So now, if I send out all the data, nothing comes back. I think, now, maybe my network is catastrophically overwhelmed, right? If one packet is lost, like perhaps one buffer is overflowed, perhaps it was just, randomly got corrupted, or one little thing went wrong. But if I receive nothing, if I just get a timeout, now I think, God, there's a lot of congestion here. So this is where the flavors of TCP come in. So what we need is another bit of paper. What we need to think of is how I evolve my window size. So roughly speaking, so I'm going to call this time, even though actually it's kind of a clock between acknowledgements. And this is the size of the congestion window, C, W, and D. Now, I'm going to start over here, weirdly, but you see why in a minute. If I send out all of my packets, we count them all out, and we count them all back, and it's success, I'm going to make my window go up a little bit. So I've counted one round of packets, they've all come back, great news. So the network's maybe it's a little bit bigger than I thought.
So you can sort of push it a bit. You think, oh, I'll try that. Try that.
Yeah, 65 miles an hour was good, let's try 70. 70 was good, let's try 75. So we're going to creep our window size up. Bam, 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 bam. Okay, it's going to get bigger and bigger. But we get a loss, we're going to slam it back down. We're actually probably going to cut it in half. So we'll make our window half as big, maybe, and creep it back up. If I get that triple duplicate, I'm going to cut it in half, bam, 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 and start creeping it back up again. Theoretically, we get this kind of sawtooth. If we get a catastrophic loss, we might want to start again, but I've left this bit because I haven't really talked about how we set off. Because what we want to do is, these windows can be quite big, they can contain quite a lot of data. And if we started with this creeping it up slowly, oh, I didn't give this a name. We should give that name. We call this AIMD, Additive Increase Multiplicative Decrease. I'm going to make the window one packet bigger if we get them all back successfully, but if I detect congestion, I'm really shut things down quick. Bam. All right? I don't want to creep things down and still keep overwhelming the overwhelmed network. So additive increase, I'm popping it up by one. Multiplicative decrease, cutting it in half. But at the start, we want to be a little more aggressive. Because if we start and we send one packet, and we send 2 packets, 3 packets, 4 packets, 5 packets.
Life's too short.
Yeah, exactly. Life is far too short. It's going to be a long while before we're sending 1,000 packets. So we have, I think maybe one of the worst names in computing, we have what we call, here we have slow start. And we call it slow start because it's tremendously quick. I don't know, I didn't name it. No, it's to get out of the slow start. So our window, I'm going to give the window in packet numbers, which I shouldn't do. It should really be in bytes, but to make it easy, so I'm going to send 1 packet, see if it comes back. Now I'm going to send 2. I'm going to send 4. I'm going to send 8. I'm going to send 16. Right. So the initial phase is exponential growth, just to get us out of that rut where things would be real slow. And then once we've had our first loss, once the connection's going properly, we're going to move into the additive increase, multiplicative decrease.
So you might shoot all the way up to 1,024, and then you have loss. So you
have loss, so we're going to drop back down and get back into this AIMD. And this is where we get into the flavors, because firstly, like, we said, okay, if we get those duplicates back, we can infer a loss. But also there might be that timeout loss where we're going to shut it down a little bit further. How long do we wait? So we think back to that round trip time. There's various algorithms involved here, but we're going to wait a kind of multiple of that round trip time. So we're going to measure, it took 0.1 seconds for all of these packets. I'm going to wait a multiple of that, and then I'm going to say, if we haven't seen any acknowledgements, something really bad's happened. So that timeout adjusts with the round trip time, and that means we can have the same algorithm working for across a data center or across to Australia, where the round trip times are very, very different. The same algorithm, or even up to a satellite, the same algorithm more or less can work. Get something sensible because they're adjusting to the round trip time. Now, people look at this and they immediately want to start tweaking with it. They're going, oh, well, look at that. Yeah, that seems like a waste, doesn't it? And over the years, the exact nature of where you finish your slow start, the exact nature of when do we halve it, when do we increase it, and this is why we end up with all of these flavors. And I say at the moment literally the flavor of the month actually is qubit, which I think People are going to kill me if I get this wrong. I think Windows, Mac, Linux are all using those. There's other things they can use. Some of those algorithms, they look at the round trip time and they say, "Oh, that round trip time's creeping up. I'm gonna shut it down in case that means congestion." So that's another way of doing it. But most of them are working on the loss of signal. So people look at this and they think, seems a bit. I could do better than that. I can probably improve on that. Maybe, what if we don't cut it in half? What if we cut in 3/4? What if we? So maybe what we need to do is look at the situation in the wild, and we'll see that it doesn't quite look like this kind of beautiful, clean picture in here. And we'll see also why, if we think about the early days, those early networks were real slow, right? You were lucky to get a few kilobits per second coming through, kilobytes per second coming through. But it's nowadays, you're going, I've got my 1 gig connection, but it's not really enough. And the same,
we all
want more bandwidth, right? Could I have 10 fibers connecting to my home? We're going to have a look in the wild, look at some actual genuine packets coming through and see that the situation for TCP is not as clean, maybe, as I presented it here.
So what do the different colours mean there then?
So these are telling us about the nature of the protocols and which particular protocol is being used for that. One, we'll see later there's some black ones indicating something's gone horribly wrong. This one's indicating that I have highlighted it. And here we're going to follow this particular stream, which I hope is the correct one. Yes, it is. So what I'm doing here, I'm grabbing a large, I think it's just over a gigabyte, data file from my virtual server in Manchester. So it's a relatively short in network terms connection. And I'm asking Wireshark, reconstruct this TCP stream. So it's finding all of the packets associated so that we can take a look at that as a conversation, starting with the SYN, ACK. But we'll see things are a little more complex than we teach them in the classroom. Here, we're finding things right at the start of this stream working like I said they would. So we've got a SYN, ACK, and an ACK. Immediately, things start to look different because we've got transport layer security on top. So this is the bit that makes it secure, but it's not part of layer 4. So we don't care about it today. But that's making it secure. So we've got a lot of cipher stuff. And now, so again, some transport layer security stuff. Here, so looking at this is the source IP 5.28.62.245. That's my server in Manchester. 192.168.68. That's a local, so that people might recognize, that's a local address on a home network. So that's my machine at home. And this is saying the server has sent 2,766 bytes of data and a 66-byte acknowledgement in response to it. Now, if you're a networks person, you'd kind of immediately be worried by that 2,766 because that's bigger than it should be. And it turns out I've got a lot of mesh stuff in my home network. So it's gluing packets together in a way I didn't expect it would. So already we're seeing something that's not quite the clean, pure network signal we might have sent. That's not what was sent over the big internet. My home network is somehow sticking them together. We've also got the thing being clocked by these TLS packets every so often. So they're sitting there providing an extra bit of security as well. So this is, we can see here, 4 reassembled TCP segments, 8,000 bytes. So that TLS is adding the extra security information related to the data which is sitting in those TCP packets. But we can see here is a packet. We can see the sequence number associated with it and the acknowledgement coming back from it. And I said this acknowledgement, when I was talking about the sequence number and acknowledgement, I was saying, I'm giving you a simplified version because these sequence numbers and acknowledgements are not 1, 2, 3, 4. They're actually telling which bytes we're looking at, and in the case of the acknowledgement, which byte we expect. Let's actually see how this TCP window shapes up. So I've written a little bit of code, and it's going to cycle through the capture file from my home network. It's going to cycle through the capture file, and it's going to ask the question, every, I think it's 100 milliseconds, how many bytes have we sent? It's going through, it's saying, since the start of the file, we've had 23 seconds, 24 seconds, here's how many bytes we saw. So it's just a little bit of Python I've thrown together. I'll give Sean the GitHub for it if you fancy playing with this on your own network. And then it's just going to spit up a simple matplotlib style graph. Let's get that bigger. And here, and we'll see, this isn't that beautiful kind of sawtooth. When this trace starts off, actually, it's taken a long while. So all right, that's not my best scale ever, megabytes per 100 milliseconds, but that's showing how many were in that 100 millisecond sample. And then the orange line, we're averaging over 10 samples to get a nicer trace out of it. When it drops down, when it slams down real low like that, well, that's indicating there was no data whatsoever in that particular 100 millisecond sample. Or, well, actually not none, but indicating a very low amount of data in that sample. But we're not seeing that additive increase, multiplicative decrease. We're seeing much, much more jaggedy, complex behavior because there's so many things going on. You know, we're competing for space with lots of people. So when a lot of people see that initial diagram, they're trying to go, oh, we could make it more efficient if we tweak this and tweak that. I'm going to show you another one. So this was downloading a data file using wget. Wget is just a command that pulls a named file off a network. So here, I'm actually downloading the latest Ubuntu distribution from their website, and it's going to go and parse them all again and throw myself up the same kind of graph. And we're going to see that kind of jaggedy behavior where we don't, in real life, see that sawtooth of hitting a limit and coming down. But actually, what you can see, which I absolutely love, is...
That's a slow start, isn't it?
Yeah, we can see the beauty. Honestly, I was so happy when I saw that. It's absolutely beautiful. I swear it's real data. I haven't faked this. It's, yeah, so it's a beautiful, beautiful slow start here, getting us up to, so given it's 100, given my stupid scale, that's about 10 megabytes per second that I'm getting through to the Ubuntu server before the slow start is starting to break down here. So we've got the beautiful slow start mechanism actually visible, which it wasn't in the previous graph. So I think we're quite lucky to capture that in the wild.
And then I'm guessing life just happens, right? Like you say, there's all sorts of things going on the internet. So it's going up and it halves. It's going up, it halves. It might go a bit further next time and less.
Yeah. So I guess my final message for this is, when we think about TCP, people come up with these kind of Byzantine, complicated, oh, well, like if you sent a signal saying there's 53% congestion on router number 5, and if we acknowledge every single packet very carefully, or you've got two problems. You've got the problem that a lot of the mechanism is fixed, right? That I showed the packet header in the previous video, and there's a little bit of space in there. There's a few bits you could use if you wanted to, but that's probably going to cause trouble because there'll be middle boxes and firewalls looking out for funny things going on with those. So if you start messing with those, maybe some middle boxes are rejecting your traffic as like, oh, what's happening here? Something dodgy, right? We'll get rid of that one. So you don't have a lot of freedom to tweak, but also you're in quite a noisy world. The real internet is really, really much more complicated than the sketches we draw out in the classroom. And in some ways, like the TCP protocol dates back to the 80s. So it was the first thing that worked, and then we're kind of, it was adapted, as if we made the Model T car, and then people say, well, why doesn't it have a cup holder? Why doesn't it have a Bluetooth? Why doesn't that TCP header it evolves real slowly. Things can change in it, but it hasn't really been able to change much since the 80s. It's gained, a couple of flags have become established, and you can't signal too much. You can't say, I'm going to add on a mechanism which is going to do all of these newfangled things that I've thought of that will fix this problem. So, in the real world, TCP does its job, and it's been doing its job very, very well for the best part of 50 years now. There's so many things I've left out of this video. There's so many things that could be added on, but I think we've seen the mechanisms that make it work. We've seen how, in real life, it's pretty complicated. It's a messy world that it's dealing with, and it's got to deal with not only this just going to some data center somewhere. It's got to deal with going across the home network, going across up to a satellite or anything like that. So despite its age, it's doing a very, very, very good and complicated job. Do with a VPN is we create like a passageway so the first router hop, the first router that our traffic pops out at is in a different country. So